Okay, I guess we can get started. Hello, folks online and people here. Welcome to the December meeting of the St. John's Centre of the Royal Astronomical Society of Canada. I'm Mike Morrow. I'm the Centre President. And I'm going to start with an acknowledgement. We respectfully acknowledge the territory in which we gather as the ancestral homelands of the Beothuk and the island of Newfoundland as the ancestral homelands of the Mi'kmaq Beothuk. We would also like to recognize the Inuit of Nunatsiavut and Nunatsiavut and the Innu of Nitassinan and their ancestors as the original people of Labrador. We strive for respectful relationships with all the peoples of this province as we search for collective healing and true reconciliation and honor this beautiful land together. So, as I said, thank you all for coming and welcome. It's great to see people. And we've got about 8 people online as well. I'm going to do a couple of announcements. Our next meeting is the 3rd Wednesday in January, which is January 15th. And the speakers, Yusuf Zazu, who Yusuf got his BSc here in 2021 in applied math and physics, and he got his MSc in scientific computing just a month or so ago. And he was working with Alex Bilo and Terence Trico, and his thesis was mapping galaxy images across ultraviolet, visible, and infrared bands using generative deep learning, which is AI. So he's going to his title is going to be AI to fill the gaps in astronomy. So we can look forward to that in January. Are there still any calendars left? Okay, forget that. You're out of luck. And so there's one calendar left, $17. Talk to Randy. You can pay by e-transfer. And Jim Johnson, you want to come on and say a few words about the AstroImaging Contest?
Yeah, sure. Do you have the slides there? Or?
Yep. Oh, hang on. Something's not happening here. I know what I'm doing wrong. Sorry. There's the slide for Yusuf. And there's the beginning of your slides, Jim. You there, Jim?
Yeah, you can go to the next one.
Okay.
All right, so 2025 AstroImaging Contest. So we decided on a submission time frame of January 1st to March 31st, so the first 3 months of 2025. As like last time, images can be submitted via the email address. We'll get to that in a minute. The images that are going to be submitted must have been captured between January 1st of this year and the end of the submission deadline, so March 31st, 2025. And just like to say, images that were submitted in previous years are invalid for present or future contest submissions. That way we just like to keep everything fresh. And yeah. So again, four categories this year: solar system, deep sky, landscape, and sketches. Images can be submitted to photos@stjohnsrasc.ca. Just make sure you include in the subject line the 2025 AstroImaging Contest submission. We would like for all images to be submitted, excuse me, to be submitted in JPEG format. Maximum of 3 images per category per person. When you do submit your image, we'd also like some information about the picture, obviously. First of all, your name and the name of the object. The date the image was taken. If it's a deep sky object, the integration time. The equipment used, so for example, a camera, mount, telescope, camera lens, those sorts of things. Any processing software that was used. You don't need to get into deep detail over your processing steps, but we would like to know like what software you used, even the software you used to acquire the images if it's a deep sky object. Next slide, Mike. Image size limit of about 20 megabytes. I
Yeah,
spoke to Randy. Sorry,
okay.
go ahead.
Yeah, I was gonna say 20 might work, but if you try and send 20, it might be tight.
Yeah, I did a test with Randy earlier
Oh,
the
okay,
week, and
sorry.
I think I sent something about 25, and that bounced back. So, and Randy had said he had received fairly large images up to around 20 megabytes. So, your mileage may vary. If it bounces back, obviously just reduce it a little bit and send it again. Judging will take place in May or sometime after submission deadline. That's still to be determined and worked out, with awards being presented at the end of or at the June meeting. And judging will be amongst St. John's Center members via online poll. And awards are still to be determined and will be announced at a later date. Having said that, I have already received some promises of some awards, and I'll keep those a secret for now.
Okay,
Any
thanks a lot, Jim.
questions?
Questions? Okay, so we will, the main thing is to know how you send your images in and the details of how we do the judging and sort of make them available to everybody. We'll figure out later on.
Just making sure all these details will be available on the website for people without any difficulty.
Yeah, I guess so. Craig, we can post this, these slides. Yeah. Okay, so, I'd like to welcome any visitors. We do have some visitors tonight, and just mention some of the benefits. The RASC, especially the center, it's a supportive community helping people learn about astronomy. One of our assets is the chat group where people can share their observations, but also do some informal mentoring. There are some publications, some low-cost equipment rentals. From time to time, Gary offers a free planetarium show for members, so that's a benefit. And we do occasionally have observing sessions out in Butterpot for members only. So there are some benefits to membership. There is a monthly bulletin that all members get, and a weekly newsletter that anyone can sign up for from the RASC. And with that, it gives me great pleasure to introduce our speaker for tonight, Dr. Ann O'Grady, for our traditional December talk, or increasingly traditional December talk. So Ann is a postdoc at McWilliams postdoc at Carnegie Mellon in Pittsburgh. She did her PhD in astronomy and astrophysics at Toronto, did her BSc in physics and applied math here, and her research involves observations of stellar populations in nearby galaxies, and she uses those observations to put constraints on rare or unknown class of massive stars. And the title is Identifying Yellow Supergiant Binaries in the Magellanic Clouds, First Results from Spectroscopy. But my understanding is that if everybody behaves, you might be getting some bonus material as well. Okay, so we need to do a little bit of technology now. So I'm going to stop sharing, and Anna's going to take over, and I'm going to pass the plug to her, and I can slide this one a bit out of your way, and you can slide more in line with the camera, and maybe. Randy, can you tell me when I'm aimed at, or when Anna...
I can move over a little bit as well.
Okay. Anyways, you can communicate with Randy about whether you're in the
Okay.
frame or not.
I'm just gonna get this sharing.
Anna's going to move over a bit more.
Yeah. Okay, and I am also did you mute yourself here, Mike, or is this still,
Oh, probably not.
okay?
Yeah, you need to be.
Yeah, I'll be in front of my laptop, so it might be best if you,
Good thinking. You must have done this.
there's a lot of Zoom in,
Let's see. Oh, okay.
right here.
There we are.
So if you just click and unclick the mute, so now hopefully, yep. And hang on, I can hear myself here. 1 second. Okay, all right. So,
Can people at home hear Anna?
yeah, can everyone
Okay.
online hear me? Thumbs up? Okay.
Yep.
Perfect. Okay. So, and that's showing. Yes, this meeting is being recorded. Okay. So, hello everyone. I want to thank Mike and the whole center for the invitation again. I think this is my 6th or 7th time talking. I have actually lost count, which I think is delightful. I'm really thrilled to be back again. This is and will remain an absolutely wonderful way for me to sort of cap off my academic year in astronomy. And I have spoken I have given talks in the United States, all across Canada, in Belgium, in Ireland, but this is my favorite place to talk, always. So, okay. I'm like 30 seconds in. So I will be giving a short update to the project that I described to all of you last year. I will be giving a recap, so if you weren't here for that, you'll be getting sort of the basics of it. But the reason why I'm giving you a short update is because this year was really, really busy. I didn't get quite as far in my yellow supergiant project as I was maybe hoping to get. And then also, there was another project that I was working on that happened very recently, within the last 2 months or so, that involves, sorry, this isn't, okay, there it is. That involves a certain large red star and maybe a much smaller companion to it. So we'll get to those in just a minute. But first, a recap of my yellow supergiant project on so title Yellow Supergiant Binaries in the Magellanic Cloud. So for those of you who are fans of science fiction, you probably are all really familiar with one really famous binary system, which is the twin suns of Tatooine. So this is a binary system. You have 2 stars that are orbiting each other, perhaps with planets around it or perhaps not. So we've all seen this popular version before. But what I study are massive stars in nearby galaxies in binary systems. So if we look at what our sort of collective understanding of the evolution of massive single stars was for a very, very long time, we can sort of summarize it in this Hertzsprung-Russell diagram. Where is my map? Okay, yeah, I'm going to use the pointer so that people online can also see it. So this diagram here is showing the temperature of stars versus their luminosity or how bright they are. And this sort of hatched in region here is the main sequence. This is where most stars spend most of their lives burning hydrogen into helium. Our sun is off this scale. You see the smallest small here is 12 solar masses, so something that's 12 times the mass of our sun. These are massive stars. These are the types of stars that I study. And it was thought that most stars are in single systems, just the one star evolving all by itself. It burns hydrogen into helium on the main sequence. It shoots across this area called the Hertzsprung gap as a yellow supergiant. And then if it's a bit of a smaller big star, it will burn helium as a red supergiant. Or if it's a really, really big star, it kind of does this weird mass thing. It turns around and it becomes a blue supergiant or a Wolf-Rayet star. However, binary star evolution can completely change what happens in the life of a star. Some binary stars the 2 stars are far enough apart from each other that they never interact. Nothing changes about them, so they're effectively single. But for some binaries, you can either exchange mass or merge. And these interactions can occur on the main sequence or when the stars have evolved. And really, really critical work that was done about a decade ago now found that 70 to 100%, so all basically massive stars, so all stars bigger than about 10 times the mass of our sun, are in binary systems. And of all of those binaries, this pie chart here represents the different types. So about 30% of them are effectively single. These are binary systems where the two stars are so far apart, they're never going to bump into each other, they're never going to do anything, they evolve as if they were by themselves. But for 71% of all these massive stars, some of them will have their envelope stripped off, some of them will accrete in something called Roche-low overflow, some of them will even merge together, where you have two stars that become one. So obviously, this changes our understanding of massive star evolution quite a bit. The simple, relatively simple lines on these diagrams don't really do justice. So yeah, we know that 70 to 100% of all massive stars, so everything in this mass range, most of them are going to be in a binary system, and 70% of those are going to interact in some way. 20 to 30% of them are going to merge on the main sequence. So for 20 to 30% of all of the stars that you might find along this massive main sequence here, they're going to merge together into one slightly bigger star early in their lives. But what about the other, 70 to 80% of these interactions? Well, some people, there have been constraints put on how many massive stars we see in binaries across this diagram. So there has been work done for red supergiants that find that 20 to 40% of red supergiants that we see in the universe are in binary systems. And for blue supergiants or Wolf-Rayet stars, we see about 30% of them are in binary systems. So you notice a really big drop here. We know that things on the main sequence in this hashed area here, 70 to 100% of them are in binaries. That then drops down to 20 to 40 or 30% after this evolution happens. So something is happening to all of these binaries. And one area in particular that interests me the most are yellow supergiants. So these are stars of intermediate temperature, around the same temperature as our sun. And as stars go across the Hertzsprung-Russell diagram, as they cool down in temperature, they expand. Essentially, they're staying at the same temperature, but they're cooling down a lot. In order for the star to stay in equilibrium, it has to expand to accommodate that temperature change. And if you have two stars in a binary and one gets really, really big, you can start to have interactions. So inside the Hertzsprung gap, there are many, many interesting types of binaries that you might find. First, you have the things that will become red supergiant binaries. We know that once you make it over to the red supergiant branch, 20 to 30% of things are still in binaries. So you should see those as yellow supergiants. You can also have interacting binaries. These are binaries that when one star is expanding, it gets to such a radius that its material starts to overflow onto its companion star. The stars start to share mass and share material between them. And what occurs here, you'll see here from this diagram, this is from a paper by Jakob Klenke, which is a really, really nice piece of work, that stars will essentially get stuck in this yellow supergiant phase. And instead of, usually when stars get to the phase where they're burning helium, they're already red supergiants. But his models have found stars that get stuck in the yellow supergiant phase at hotter temperatures, and that's when they begin their helium burning, which is very strange and not something that we predict in single star evolution. You also have post-interaction binaries. So for some binaries that their interaction began early on in the main sequence, they started on the hydrogen main sequence and they became stripped stars. The hydrogen envelope of that star was completely removed, and you're left with just a star of helium and a couple of heavier elements. These helium stars, once they begin their second round of burning, they will expand again, recross the gap, and sort of masquerade as yellow supergiants. These are essentially stars that look like yellow supergiants to us. They're luminous, they're in the right temperature range, but they're not yellow supergiants at all. There are these things called helium giants. these stars are completely devoid of hydrogen. You consider that most things in the universe are about 75% hydrogen, 24% helium, 1% whatever. These stars are completely missing that 75% of hydrogen that most other stars and gas giants and so on have. And without really detailed spectroscopy, you would just think that it's a normal yellow supergiant, just like anything else. And finally, there are certain supernovae, so massive stars that explode at the end of their lives. Most supernovae, if you go back and you look in old Hubble archival photography, old space telescope images, and you look at the area of the sky where the explosion was, most times you'll see a red supergiant. We're really confident that a lot of supernovae come from red supergiants. But in some of these cases, when we've gone back and looked after certain supernovae have exploded, we've seen yellow stars. We've seen yellow supergiants. And it's thought that the only way to explain how you get a yellow supergiant blowing up as a supernovae kind of early before it becomes red is by essentially the process that Jakob Klemke explained, where the star gets stuck as a yellow supergiant. It can't make it to the red supergiant branch and it explodes there. This is a whole lot of information. This is bridging many, many, many types of astrophysics, but all of this is to say is that there's a lot of interesting stuff that happens in this bright yellow part of sort of stellar phase space. So understanding yellow supergiant binaries is totally crucial to understanding the full landscape of massive star binarity. However, while we know of a couple of examples of yellow supergiant binaries, no one has ever done a systematic identification of all yellow supergiants and how many of them are in binaries. If you remember earlier, I talked about people worked really hard to figure out that 20 to 40% of red supergiants have binaries, 30% of blue supergiants have binaries. No one has figured out that percentage yet for yellow supergiants. So that is where myself and my collaborators came in. This is a project that I began as a PhD student and I'm still working on now. We want to understand if you take every single yellow supergiant that are in the Magellanic Clouds, or the Magellanic Clouds are these little satellite galaxies of our Milky Way, kind of like how the moon is a satellite of Earth. If you look at every single yellow supergiant in the clouds, how many of them have a partner? How many of them have a binary companion? And once we figure out that binary fraction, can we identify systems that are currently interacting? Can we identify any of those weird helium giants, those things that pretend to be yellow supergiants but are actually totally weird? Can we identify any partially stripped stars that we think would, a long, long time from now, blow up as these interesting supernovae? So the goal for this project was to first understand what types of yellow supergiant binary systems we could identify with the resources that we had easily available to us. And what I mean there is archival photometry. All sky surveys that telescopes and space telescopes spent a long time sort of mapping the entire sky. To put this quickly, we looked in the Magellanic Clouds, which are these two galaxies, and searched for yellow supergiants that had sign of a binary companion. And for various evolutionary reasons, we are pretty sure that the companions of yellow supergiants should be B or O type main sequence stars. Our sun is a G type main sequence star. It's yellow. O and B type stars are blue. So you have a yellow supergiant with a smaller but much bluer star. And that motivated how we were going to search for it. In this plot here, what I'm plotting on the horizontal axis is the redness of a star. So this is a red color, and over to the right is more red. Bluer on the left, redder on the right. On the vertical axis, I'm plotting a very blue color, where again, bluer is to the bottom and redder is to the top. So the bluest things are down in the corner, the reddest things are up in the top right corner. And what I'm showing here, these are models of blue main sequence stars. So these are the things that we think are the little companions to our yellow supergiants. These bigger circles up here, these are our yellow supergiants. you can see that the B-type main sequence stars are all the way down on the left here. They are extremely blue, whereas the yellow supergiant models spread out a lot more. And then if I combine those models together, there's essentially an area of this plot where we expect yellow supergiants that have main sequence companions to lie. In this vertical axis, in this blue color, you essentially can tell the difference between a yellow supergiant that it's all by itself versus a yellow supergiant that has a little buddy with it that's very blue in color. So we were thinking essentially that we could use these colors, which are widely available for a lot of stars, to identify the best candidates of yellow supergiants that have a blue excess or a companion to them. So briefly, this is showing you the small Magellanic Cloud. This is showing you the large Magellanic Cloud. You can see there are many more stars. And the gray dots here are every single yellow supergiant that we think we know about in the Magellanic Clouds. The ones that I'm coloring in blue here are essentially too blue, too hot for me to discern anything about. Those might be something that I'll come back to in future work, but not something that I'm worrying about right now. The yellow ones here, these are yellow supergiants that when I compare them to our models, they match up really well with just the yellow supergiant model, nothing added in. They look like yellow supergiants all by themselves. And then these green stars down here, their red colors make them look like yellow supergiants, but when you look in the blue, they have way too much blue light to be a yellow supergiant all by itself. There has to be something else there that's contributing all of that blue light to the star. And we think that that means that these are yellow supergiant binaries. So can we find yellow supergiant binaries with photometry? Yes. Okay, but what are these really? The data that I'm showing here are just 4 colors, essentially taking a picture with 4 different filters, 2 red, 2 blue, and making an assertion based off of that. In order to understand what each of these little dots, what each of these little star systems really are, we have to look at spectroscopy. This is when you put a prism in front of your telescope and spread out the light from a star into all of its constituent colors, like a prism. And that allows you to tell what elements are inside of that star or on the surface of that star. And there's a reason that we're doing that. This is a basic diagram of the types of elements that appear in the spectrum of a star based on how hot the star is. So cold stars here on the right and hot stars on the left. And we have the spectral type down here. The sun is somewhere in here. So if I put this down here, this yellow box represents the temperature range of yellow supergiants that I was looking at. So from 4,000 Kelvin all the way up to about 9,000 Kelvin. The blue box here, that's about how hot I think the companion should be. These little blue main sequence stars are really, 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 really hot, about 20,000 Kelvin and a little bit beyond this plot, actually, up to about 75,000 Kelvin. So you can see that what this is showing is the strength of different elements you'll see in these stars based on their temperature. And you can see that the elements that you get in these stars are different, mostly. If you just look at the cold end of yellow supergiants, you can see that you get a lot of different metal lines. Ca2 here, this is calcium. There's a lot of calcium lines in cold yellow supergiants. There's a lot of iron lines. So you get these metals. And the reason that you get metals in colder stars is that the cooler, relatively, this is still 5,000 Kelvin, it's incredibly hot. But in terms of stars, the cooler temperatures allow more complex elements and complex molecules to exist without being blasted apart, essentially. Whereas the hotter and hotter you get, the harder and harder it is for things more complicated than hydrogen or helium to survive. So that's why for our blue stars, you really only get some hydrogen and some helium. So in the case, when we're looking at a yellow supergiant that is relatively cold, so about 6,000 Kelvin or below, we can look for the presence of hydrogen lines. Essentially, if we know that we're looking at a 5,000 Kelvin yellow supergiant and we see hydrogen, there's absolutely no way that's coming from the yellow supergiant. It physically can't. Our understanding of stellar nucleosynthesis says that that hydrogen has to be coming from something way, 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 way hotter, a companion star. However, things get a lot trickier on the hotter end of the range that I was looking at. Remember, I was looking at yellow supergiants up to about 9,000 Kelvin. And when you get to those temperatures, well, hydrogen, yellow supergiants start to have a lot of hydrogen in their spectrum as well. The same or even more hydrogen if you consider the height of this line compared to this. So for yellow supergiants that are really hot, looking for hydrogen isn't going to cut it. You expect hydrogen to be there. That doesn't tell you anything. However, that's when we look for helium lines. And we can do this as well in the other case, but it's essential here. Ionized helium will only ever appear in stars that are about 25,000 Kelvin or hotter. Ionized helium is really hard to look for. It's a very faint signature. It's not as obvious as hydrogen, but it's what to look out for. This is just an example of what I was just talking about with modeling. So this isn't real data. I'm going to show you some real data really soon. But what we're essentially showing here is the red line is a yellow supergiant and the blue line is an O-type main sequence star. And in the scenario where you have a cold yellow supergiant, like about 4,000 Kelvin, you can see that the strength of the blue line overtakes the red line at blue temperatures, and you get these hydrogen bomber lines. But for a hot yellow supergiant, for an 8,000 or 9,000 Kelvin supergiant, you can see that the yellow supergiant just completely overpowers everything here. There's no way that you can see in these large lines this hydrogen. However, and I'll show you the proof in the pudding in just a moment, there are really faint helium lines that, yes, we think that we can see even in all of this mess up here. So, with some really big telescopes, mostly the two Magellan telescopes at Las Campanas Observatory in Chile, which I've been very fortunate to visit a few times, I was able to get spectroscopy of basically all of the green stars. I'll just roll back real quick. Basically all of the green stars here. Oh, sorry. Don't know why that went back. Basically all of these stars here, I have spectroscopy of, and I'll show you just a couple of them. So what's in black here? This is real data. We sat on a telescope. We pointed it towards one of the yellow supergiants that I thought was interesting. We let that light come into the dome of the telescope and we spread it out using a spectrometer. Automatically, of course, I wasn't like doing this. This is just for dramatic effect. But this is real starlight that we've spread out to try and understand what kind of elements are inside of it. And then the colored lines here are different models. The orange line is a model of a yellow supergiant. And you can tell that the orange line fits it okay, sort of at the hotter end, but when you, or sorry, at the colder end. But when you get down here, where this black data is here, the orange line doesn't cut it at all. It doesn't get close. You have to add this blue line, and this blue line is an OB main sequence star. So to recreate this real data of a star, you have to combine two stellar models together. This is definitive proof that this is a yellow supergiant binary. We found one. We found a lot. I have confirmed now, I'm going to say about 20 to 30 at the moment. I have more data coming in from the semester that I'll look at that I'm feeling confident about. Previous to this, there were maybe 5 or 6 confirmed. So we've done a huge amount of work increasing the number of confirmed yellow supergiant binaries. The same thing happens here. This fit isn't great. You can tell the green line is what I'm saying is my fit. It's not amazing, but you can still tell that there's a complexity here in the lines that doesn't get created with the orange line, and you really need that blue line to sort of kick up. So that's another example. So, sorry, I'll just back up here for a second. This was an example of these colder stars, where the yellow supergiant is really powerful at colder temperatures, and the, they're sort of evenly matched at this hotter range here. So you can actually see the presence of the B-type star. This is an example of a hot yellow supergiant. You see the green data here, the green line here is now the data. You see these big steep lines, these big troughs in the data. That's the hydrogen Balmer series that is coming from the yellow supergiant. We can't use that to detect the presence of the little companion anymore. However, as I mentioned, there are these really faint helium lines that will never show up in a yellow supergiant, but will always show up in an OB star. And if we zoom in on this tiny little area here, that's this box right here, and there's this little dip in the spectrum. And that little dip is helium-1. And the presence of this little dip in the data, and we're sure that it's real, it's not like detector noise, this tells us that there has to be an incredibly hot star along with the relatively hot yellow supergiant. These are spectra of 6 more really hot yellow supergiants all lined up on that helium line. And you can see some of them, it's extremely dramatic, but you see this line appearing in all of them. So even in the case of hot yellow supergiants, we are absolutely confirming the existence of these yellow supergiant binaries. I'm going to show you one more thing. This plot is kind of bad. It's from my sort of preliminary software I used to look at it. And this is because I can't get anything to fit to this star. I try fitting all of my models. I can get a yellow supergiant to fit out here. It's okay. But look at what's happening here at the end. If I back up to this hot star here, see the spectrum, it dips down. This is something called the Balmer break. But out here at the very end, the spectrum is staying mostly flat. And you can see the model of the blue star along with it is doing kind of the same thing. But in this one here, in this particular star here, it's going back up. None of the OB star models that I have are tilted basically high enough to get this to work. So I don't know what this is. This is really interesting. You can see here as well that the width of the hydrogen Balmer lines is very, very, very thin. And if the lines are really, really thin, that means that the yellow supergiant is very, very big. It's very puffy. It's very inflated. I showed this spectrum to someone who is an expert in those helium giants I was thinking about that I was talking about before. These stars that are masquerading as yellow supergiants, but are actually these giant puffed up balls of helium. And she thinks that this might be an example of a helium giant, maybe. So this is super weird. I can't tell you exactly what it is because I can't get any of my models to fit, but it might be something really cool. So to just walk you through a little bit of future work, the main goal of my project is still to answer the question, if you take all of the yellow supergiants in the clouds, how many of them have friends? What is the binary fraction of yellow supergiants? This is a really important benchmark for binary population synthesis models. People who essentially model entire galaxies or entire universes of stars, they need to know when they're making their fake little model universes, how many yellow supergiants are in binaries, and no one has answered this question before. I want to identify yellow supergiants with partially stripped envelopes. These are the yellow supergiants that might explode into these weird types of supernovae. Also looking for these helium giants. And then finally, I should have got this text down. This is a lot, but basically there's this prediction that if you go to lower and lower metallicity, or essentially if the stars have less and less and less elements heavier than helium, if it has less iron, less carbon, etc., if it's more pure, if it's more hydrogen and helium, you expect more stars that only get a little bit stripped and stay as yellow supergiants, and fewer stars that get really stripped and end up as helium giants. I should be able to couple my work with previous work that has been done before on these fully stripped stars and basically come up with some sort of prescription for the efficiency of binary stripping across different metallicities, which that's a really long-term goal, but it is something that's cool and important in the field, basically. So I know that was a little bit of a whirlwind, But the upshot, basically, of what I wanted to tell you in terms of the yellow supergiant project is that things are going well. The spectroscopy that we have absolutely confirms that we have found a bunch of yellow supergiant binaries, which is really, really exciting. Now for something a little bit different. What I'm going to show you now is I'm going to give you some background, but is extremely preliminary data. It is brand new science, as in like 2 days ago. It's not a solid result yet, but I'm very excited to share. I am going to talk to you about finding Betelgeuse's buddy. So, darn, hang on. 1 second. Okay. I worked really hard on that animation. I didn't want to skip it. So, Betelgeuse having a buddy, just real quick, hands up, parents don't count. How many of you have heard about this in the news or on science stuff like somewhat recently? Okay, cool. Some of you have heard about it. Okay, if you haven't heard about it, don't worry, I'm going to explain it to you. But this basically, when I saw this paper, this result pop up in sort of my daily news feed, I said, this is the craziest thing I've ever heard of, and I want to be a part of it. So, Betelgeuse, the right shoulder of Orion the Hunter, the closest red supergiant to Earth, the 10th brightest star in our sky. There have been innumerable observations of this star from time immemorial. It's hard to see, I apologize, but the first date on this plot here is from 1900. These are visual approximations of the brightness of Betelgeuse. This is just someone looking up in the sky and saying, I think it's about this bright. The green that you start to see over here are filter observations. So like putting a V-band or an R filter on your telescope. This light curve is from the American Association of Variable Star Observers. Betelgeuse is a variable star. That'll be important in just a moment. And the vast majority of these observations are from amateur astronomical observers over the years. And the neat thing about the AAVSO website is that it lets you look up the name and the association of the people who sent in the data. And I did a little search. And I'm hoping that maybe there are some familiar names up on this sheet, but there are many a RASC member who has observed Betelgeuse over the years. So local contributions to this star abound. So in 2020, early 2020, Betelgeuse decided to be a little bit of a drama queen, and it underwent something called a great dimming event. I'm sure many of you were made aware of this. There was this absolutely dramatic drop in brightness from where Betelgeuse was normally supposed to be. The picture on the left here is from like 2018 or something, I think, and then the picture on the right is from 2020 in the midst of this, and you can just see the difference in the brightness, just the overall spread of Betelgeuse. I saw this for myself. I happened to be at Las Campanas Observatory when this was happening, so really, really clear skies, and I went out one night and I looked up and I'm like, oh yeah, that is dimmer. That is not the brightness that Betelgeuse was supposed to be. A lot of people thought that this meant that it was going to blow up. It did not blow up. A lot of work went into figuring out why did this happen? Why did Betelgeuse suddenly get a whole lot dimmer? The consensus after you can see that this paper was from this year, many years of work and many minds, was essentially that Betelgeuse had some indigestion, basically, burped up a big dust cloud, and the dust cloud is why the brightness dropped so dramatically. So an interesting science case. However, I'm not going to talk more about the great dimming at the moment, but just use it as context to essentially say the great dimming spawned a ton of new interest in Betelgeuse. A lot of people started looking back at this closest red supergiant to Earth and asking age-old questions that had never been answered before about our nearest big red neighbor. One of those questions was about the nature of Betelgeuse's long secondary period. So I said that Betelgeuse is a variable star. That means its brightness goes up and down over time, like a dimmer switch in your hall. You can turn it up and down. Betelgeuse is doing that. It has what's called a primary period of about 400 days. That's sort of this in the blue. You can see it going up and down and up and down and up and down. the time distance between each of these little peaks is about 400 days. But if you spread out the entire light curve of Betelgeuse, you can see it's faint, but you can see that there is this overall other modulation, that whole light curve itself, while it's going up and down every 400 years, has this more gradual wave to it. That wave is 6 years long. So it's really hard to see. Betelgeuse is one of the few stars that we know does this because we have so much information about it. And this long secondary period is also visible in the radial velocity curve of Betelgeuse. So when I talk about radial velocity, when Betelgeuse pulsates, it's changing its brightness because it's pulsating. It's getting a little bit bigger and a little bit smaller, a little bit bigger, a little bit smaller. So when it does that, both its surface area increases, so you get more light coming at you, but also the surface of Betelgeuse is physically moving when that happens. And you can measure that speed, and you can measure what is essentially a Doppler effect. The best example that a lot of us hear of Doppler effect is the audio Doppler effect. When an ambulance goes by you, it's when it passes you. The sound waves are being compressed and then stretched out as it's coming towards you or going away from you. The exact same thing happens with light, and we see subtle differences in the light from Betelgeuse when it's expanding towards us and when it's coming back. And we see this long secondary period inside the radial velocity as well. So we know that this happens on Betelgeuse. We know it happens on a few other large red stars as well, but we have no idea where it comes from. And the reason for Betelgeuse's long secondary period has been debated for literal decades. And then in September of this year, a paper came out on the archive, which is where new sort of articles, new ideas come out. And this paper is called A Buddy for Betelgeuse, Binarity as the Origin of the Long Secondary Period in Alpha Orionis, also known as Betelgeuse. So this paper basically walks through every single possible explanation for why Betelgeuse has this 6-year-long secondary period. It walks through every explanation that anyone has ever thought of, and it exhaustively proves why every single one of those explanations is wrong. There's some piece of evidence that proves that it's wrong, except that Betelgeuse has a little friend. And critically, the lead author of this paper, Jared Goldberg, coined the name Beetle Buddy for this little star. So we're going to be calling Betelgeuse's companion Beetle Buddy because I think that's adorable. So, as I mentioned, this paper walks through literally every idea that anyone has ever had as to why Betelgeuse has this 6-year-long period in it. And it explains why they all don't work. I'm just really going to briefly talk about convection for a second, mostly just because I want to show off some cool videos. This is an image of our sun. This is really, really zoomed in. It's a really small area of the sun, and we have these kernels. These are convective cells within our sun, showing the overturning of these great gaseous sort of fonts of matter inside the sun. And the size of one of these cells is about the size of a large city, like Manhattan. So that's how big one of those cells are on the sun. That is our sun. This is a simulation. Great. This is a simulation of the convection of a star like Betelgeuse. This is the entire star being simulated, and you can see these gargantuan ebbs and flows, these huge cells that pop out of the star. That's the size of our Earth compared to one of these. You can fit an entire planet inside of these convective zones. So one of the thoughts was that the long secondary period of Betelgeuse was caused by regular motion in these convective cells. But Jared and company who worked on this paper showed that that was not the case, that giant convective cells could not explain the persistence of this long secondary period. Convection is random. It happens over time. You get random bubbles in random places. It can't explain this nice, smooth 6-year-long period. So I love tables like this because it really showed that the astronomers did the work. They worked through absolutely everything, and there is only one possible explanation that ticks off every single piece of evidence in this long secondary period, and that is binarity with dust modulation, which I'll explain what that means in a second. Essentially, what they looked at was that if you compare where the very peak of the light curve is, so where Betelgeuse is at its brightest, which is the orange line here, and then you compare the peak of the radial velocity curve, so that's when Betelgeuse is moving towards us at its fastest, they are offset. They're not right on top of each other. There's a little gap in between them. The peak of the bottom curve, you can see, is right here. This is a peak, this is a peak, whereas the peak of the top curve is right here, and there's this little gap between them. If you thought that Betelgeuse was alone, and that the long secondary period in the radial velocity was just caused by some pulsation that was happening over the course of 6 years, you would expect the peak of the light curve and the peak of the radial velocity to be exactly out of phase. And they're not. They're about a third of a phase out of phase. There is some extremely complicated geometry that went into making this figure, and geometry was my least favorite part of math, so I will not be explaining the details of this, but essentially, Jared and his co-writers basically did a really, really elegant work of math to prove that the only way that you can explain all of the other evidence, plus this 1/3 offset in the difference between the light and the speed of Betelgeuse's velocity, the only way that you can explain it is if there is a binary companion to Betelgeuse, and it is behind Betelgeuse at minimum light, or when the light is darkest, and in front of Betelgeuse when the light is at its brightest. They have this great little schematic in their paper, which I also love because this made everything super, super clear to me. Up on top here, you have the light curve, and on bottom, you have the radial velocity. And in the middle, this is a little schematic of the system. You have Betelgeuse in red. You have all of this dust around it. Betelgeuse as a red supergiant is extremely dusty. We know this from a lot of observations. And there's this little star that's orbiting it. And this little star, essentially, the star is shining. It's bright. It is able to burn away a little pocket around itself. It's able to get rid of the dust that's right next to itself, so that when it swings around and it's in front of Betelgeuse, it is essentially carved a little hole in the dust that allows more of Betelgeuse's light through, which is why the light curve is at a maximum. And then the relative motions of these explain why the radial velocity is at a maximum at these phases. Again, if people are interested in a little bit more of the technical details, I can explain them later, but essentially, this is an incredibly elegant solution, and I, along with a lot of people, are completely convinced by the thoroughness of this study that this has to be the explanation for why Betelgeuse's long secondary period exists. They did some work to explain the properties of Beetle Buddy. So they think that the mass of Beetle Buddy is about 1.17. So we're going to round that to 1 just to be easy, about the same mass of our sun. So Betelgeuse, the red supergiant, has a sun orbiting around it, which is kind of funky to think about. And it thinks that the orbital separation, this is a very large number. What this essentially means is that it's at about twice the radius of Betelgeuse. So pretty close to it, all things considered. This was then pretty funny. I read this paper from Jared at Journal Club, and a colleague and mine were talking about it. We thought it was really interesting. And then literally like 5 days later, another paper came out talking about the same thing from different authors. This is from Morgan McLeod and company. These are people at the Center for Astrophysics at Harvard. They tackled this question from a slightly different perspective. They used astrometry, which is literally the movement of Betelgeuse on the sky, which is incredibly precise. I haven't read the details of this paper quite enough, but they came to the exact same conclusion. Betelgeuse has to have a companion. They estimated it to be a little bit smaller, about half the mass of our sun, and that'll be important for later. But yeah, this was hilarious. These two groups of people were not in collaboration with each other. They were not talking to each other. They independently came to the exact same conclusion at basically the exact same time, which when this happens in astronomy is always kind of fun. So this is really interesting. So then the question becomes, well, from this little schematic, you have this eyeball over here, you know, eyeball seeing, can we see it? Is there any way that we could ever see Beetle Buddy? We've inferred that it exists because of subtle differences in the light of Betelgeuse and subtle ways that Betelgeuse is kind of rattling around up there. But could we ever see Beetle Buddy? Well, it's tough. From the McLeod paper, this is a really nice demonstration here of these curves here are essentially the spectral energy or the light from the star. Betelgeuse is up here. You can see it's very tall. It has a lot of energy. And then their proposed companion is down here. And you can see there's a really big gap between these two. That means that you would essentially be looking for a 40-watt light bulb that was placed directly next to one of those gigantic football stadium lights in New York, and you are in California, and you are trying to see that little light bulb next to the gigantic football stadium light. So not really possible, maybe. One critical thing that we noticed, however, was this line. This was in Jared Goldberg's paper, that the day, year, and month of the next RV minimum, December 6th, 2024. That was like 2 weeks ago. RV minimum. Okay, let's look at the RV curve. It's when it's at the bottom. Okay, it's down here at the bottom. And like this, where Betelgeuse and Beetle Buddy are separated the most from our point of view. So on the sky, you have Betelgeuse and Beetle Buddy, and it's essentially doing this. It's going around and around and around. And on December 6th, if y'all are the Earth, Beetle Buddy is right here, separated from Betelgeuse, as much as we can possibly get it to be. So after reading this paper, myself and my colleague Brendan O'Connor, who's a McWilliams fellow like me, we sat together and thought, okay, this is a little crazy, but what if we combined our powers? Brendan has a lot of observational expertise, and I have a lot of spectral stellar expertise. What if we reach out to the authors of the original studies? This is people from the Flatiron Institute of Astrophysics in New York, the University of Wyoming, Konkali University in Hungary, people from all over the world with grand astronomical expertise, experts from the Space Telescope Science Institute. And what if we ask really, really nicely if the Hubble Space Telescope and if the Chandra X-ray Observatory will look at this for us on or about December 6th? Let's find out. So myself and my colleagues at Carnegie Mellon, we reached out to the original study authors, Goldberg and all, and they agreed to let us come on. They were thinking about this as well. They were thinking about Hubble. We were also thinking about X-rays. I'll explain why we were thinking about that in a second. And they said, sure, come on, we appreciate your expertise. Let's work together. So this was in early October. And in order to meet the date of early December and making sure that we had enough time for the review process, we basically had about 2.5 weeks to put together a proposal to ask really nicely if the Hubble telescope would, like, on really short notice, look at this for us. So there's one thing that I want to talk about that was critical for us sort of getting our proposals in order. Betelgeuse, the red supergiant, is about 10 million years old. There's lots of reasons why we know that. We know that fairly certain that Betelgeuse is about 10 million years old. So that makes Beetle Buddy what exactly? We know that it's about 1 solar mass. If we assume that Betelgeuse and Beetle Buddy are in a binary, that means that they were formed at the exact same time. So from the moment that these two clouds of dust started to collapse together, 10 million years have passed. Betelgeuse is now a red supergiant. What's Beetle Buddy doing? Where is it at in its evolution? These are just from Wikipedia. If you look at solar masses here, Betelgeuse is about 17 solar masses, so it's somewhere in between these two. So somewhere around, say, it'll live for probably about 15 or 16 million years. It's at 10 million years right now. A 1 solar mass star will live for 10 billion years. That's a lot longer than 10 or 20 million years. This plot over here, this is a little complex, but essentially what it's showing is the pre-main sequence track. Essentially, stars form out of gas clouds. those gas clouds will collapse down. And as they collapse, they become denser and denser. And as things get denser, they become hotter and hotter and hotter. Eventually, they become so dense and hot that hydrogen fusion turns on in their cores, and you have a star. On this plot, that moment is sort of this leftward part of the graph here, where all the numbers are. Once you start up here at the top, and you drop down these blue lines, and once you reach the bottom, you have become a star. Okay, let's look at the 1 solar mass track. We think that's about how big Beetle Buddy is. And then we need to look here for these red lines of time. 10 million years is 1 with 7 zeros after it. So we're looking at 10 to the 7 years. And then we're right here. So the cloud of gas that formed Beetle Buddy, with the age of Betelgeuse that we know, being 10 million years old, that cloud of gas hasn't gotten dense enough to be a star yet. Beetle Buddy is not yet fusing hydrogen. Technically, Beetle Buddy is not a star. It is a protostar. It's even worse if you take the 0.6 solar mass thing. It's further up the track. Beetle Buddy is a pre-main sequence star. This really changes what we're looking for, because pre-main sequence stars look totally different than regular stars. Like, we're not looking essentially for our sun around Betelgeuse. We're looking for this pre-main sequence star. So, for the Hubble Space Telescope, sorry, not cooperating. Okay. For the Hubble Space Telescope, we wanted to look into the far ultraviolet. Betelgeuse is at its brightest at red colors, at red temperatures, so we wanted to go as blue as possible. When you get out to the bluest wavelengths, you are looking at the hottest parts of the star. And for all stars, the part of it that's actually the hottest is not the surface, it's the upper atmosphere, or the corona. For those of you who were able to see the solar eclipse this year, that moment that the moon eclipsed the sun and you saw this beautiful web of white light around the star, that is the corona and the chromosphere of our sun. It is this that we were going to go looking for. And essentially what we were going to look for is a little bit of a fluctuation of signal that could indicate that we were seeing the corona of Beetle Buddy, a pre-main sequence star, in amongst the mess of the corona of Betelgeuse. In this plot here on the right, this black curve is HST data of Betelgeuse from 2011, at not a good time to be looking for Beetle Buddy. And the yellow, orange, and red lines down here, these are HST spectrum of pre-main sequence stars that I moved to essentially be at the same distance of Betelgeuse. So you see that you're not just going to be able to see the signal. These are much lower on the plot than Betelgeuse. But there are a couple of areas, like here, for example, that the lines, especially the chromospheric emission line of hydrogen in this pre-main sequence star, is just as powerful as Betelgeuse. I'm showing this here on the left, that essentially the areas where the orange line gets higher than the black line are areas that we think, if Beetle Buddy exists, which we think it does, we should be able to see it in the spectrum. I'm only showing here the about 1.5 solar mass and 1 solar mass cases. The case of a 0.6 solar star, pre-main sequence star, is really dire. That's the red curve down here. Do you see how low this is? Based on this estimation, if Beetle Buddy is a 0.6 solar mass protostar, which is what the second paper thought, we're probably not going to be able to see it. But if Jared is right, we probably will be able to see it. So we designed this observing plan. The red circle here at the middle is Betelgeuse, and these purple squares are the detector chips for Hubble. We decided to ask for 4 observations where we essentially tile around Betelgeuse. We know that Beetle Buddy should be at about 2 solar radii, but we don't know in which quadrant it's supposed to be. We don't know if it's going to be over here. If it's going to be over here, it's going to be right here. So what we're essentially hoping is that we get these 4 images of the corona of Betelgeuse, and that one of them is going to look weird compared to the other 3. because in one of these, there's a beetle buddy, and in the other three, there's not. For Chandra, so the Chandra X-ray Observatory looks at X-rays, which are way more powerful than even ultraviolet light, what we can see with our eyes. Chandra has looked at Betelgeuse before, but out of a really, really weird coincidence, it was basically always looking at Betelgeuse when Beetle Buddy was predicted to be directly behind it, which is a freaky coincidence. But this gave us good enough justification basically to ask for an observation on December 6th or thereabouts when it came out. And what we were looking for there, this graph is the X-ray luminosity of young stellar objects about the size of the sun. Young stellar objects glow in X-ray because of the accretion disk of the gas that's collapsing down onto them is really, really, really hot. So you can see it in X-rays. And we expect Beetle Buddy's luminosity to be right around here. And previous observations of Chandra, again, were either when Beetle Buddy literally was not visible or it was not shallow. It was too shallow. It wasn't getting down to this data. So myself, my colleagues at CMU, and then the colleagues on the other paper, we worked really, really hard to put together these two observations, asking Hubble and asking Chandra. It's something called director's discretionary time. Usually for these telescopes, once per year, usually in the spring, you put in a big proposal as to what you want to look at, and you get approved or you get disapproved, and that sets the schedule for the entire year for the space telescope. But there's an understanding that sometimes interesting things happen, sometimes things blow up in the sky, etc. And director's discretionary time is meant to be essentially, we want to look at this and we can't wait to put in a proposal next year. This has to happen now. And because we knew that December 6th was sort of the important day, we knew it had to happen. So we put in these observations, we put in these requests, and then something absolutely amazing happened. We got on Jeopardy. This is real. This was a real Jeopardy question from a few weeks ago. A new study says that this red supergiant in Orion may be a binary star. It's okay to say its name twice, but please stop there, referring, of course, to the famous movie Betelgeuse, Betelgeuse, Betelgeuse. But so this was hilarious. This felt like really making it, especially for Jared, the author of the original study. He was like, you know, I'm happy about many things, but I think I'm the most happy about getting on Jeopardy. But then what made us even more happy was that we were successful on both counts. This is the email that we got from Hubble. This was really funny to me. Hubble is really, really old, and it has reduced sort of gyroscopic capabilities of moving around. And they make sure they need to tell you that first. Hubble is in reduced gyro mode. You need to know that. Oh, by the way, you've been awarded 4 orbits of Hubble. Good job. The Chandra one was interesting. Chandra has a lot more of a back and forth. You speak directly to the people who command Chandra, basically, and they really want to know if you've done your due diligence. So myself and Brendan, who mercifully is an expert on Chandra, really made the case for them. And they said, thank you very much for the detailed responses you provided. We remain skeptical of the detection, but we recognize the potential importance of it. So we're going to give you the time that you asked for. So tough crowd, but it went through. So this data has come in over the past like 3 weeks. It's most of what I've been working on. So this is extremely preliminary. I don't have final results to show you, but I still have something to show you. So HST far UV spectroscopy. This is the Lyman alpha line. This is hydrogen. The 4 colors represent those 4 quadrants of Betelgeuse that we were looking at. We have an idea, actually. I said that we didn't know where Beetle Buddy was supposed to be. We actually think we know which way Betelgeuse is rotating on the sky. And if that's true, we expect it to be in the east quadrant or the red one. Do you guys see like a really big difference between the red one and all the others? Not really. For the reason that these systems are orbiting around each other. So at this moment on December 6th, Betelgeuse is coming towards us a little bit. Beetle Buddy is moving away from us because they're in their orbit. Beetle Buddy is a lot smaller. It's moving faster. If Beetle Buddy was there and was at a mass high enough to have a prominent Lyman alpha line, there should be a spike in the red right where this pink line is. And there's nothing there. So probably it's not a solar mass pre-main sequence star based on the Hubble data. What about Chandra? This came in 2 days ago. This is Chandra data. And where there are dots, that means that there are X-ray sources. Where is Betelgeuse in this image? Right here. Probably not a solar mass main sequence star. However, what does this mean? First of all, Beetle Buddy is not some sort of compact object. There was some theory that maybe Beetle Buddy was a neutron star. So essentially, instead of being a much younger star than Betelgeuse, still forming out of the interstellar medium, it was actually the remnant of a previously much more larger star. If there was a neutron star embedded in the dust of Betelgeuse, there is no way that we would not have seen a blaring X-ray signal from it. So we know that it's not super crazy. I'm a little sad because if it had been a neutron star, we definitely all would have been on like CNN talking about this. But Beetle Buddy is really small. We don't see it in these images. We didn't see it in Hubble, and we didn't see it in Chandra. And while that's a little disappointing, as I said earlier, we are so confident in the analysis that Jared and his co-authors made. We know that Beetle Buddy has to exist. So that means that we can say how big it must be, or how big it mustn't be, essentially. If we don't see that hydrogen Lyman alpha line, if we don't see those X-rays, it has to be small. It's probably closer to the 0.6 solar mass estimate that second paper came up with, that Morgan McLeod paper from the CFA. A 0.6 solar mass star, protostar, orbiting a 17 solar mass red supergiant. That mass ratio is crazy. We think that when most stars are in binaries, the two stars are of similar mass. This is crazy. Betelgeuse is 28 times more massive than Beetle Buddy. This has really, really, really interesting implications for binary star evolution, all the stuff that I've been talking about before. So in terms of some very brief future work here, as I said, what I just showed you is like literally brand new data. We're still working on this. We are going to compare the HST data to a wider range of pre-main sequence models. We're going to scale it with how much dust we think is around Betelgeuse. Betelgeuse is incredibly dusty, but many, many people have done a lot of work characterizing that dust. So we can make a really good model of how that dust is attenuating the light. And we think we can make a really strong constraint on what mass Beetle Buddy cannot be because we don't see it in the data. For Chandra, exact same thing, but we're probing different physics, accretion, winds, etc. Do we get the same maximum mass constraint from the Chandra data? Yes or no? There's an interesting science question there. And finally, this is the first time that anyone has ever done this like 4-quadrant view of Betelgeuse. Even if we can't see Beetle Buddy, we still have relatively contemporaneous, the data were taken just over a couple of days of each other. We are looking at 4 different sections of the corona of Betelgeuse. And we know that in stars like our sun, the wind that's coming off of it, that beautiful sort of airy white corona that you all hopefully saw during the eclipse, it wasn't isotropic, it wasn't the same everywhere. There were little twists and knobs in it, it looked different. This is probably going to be the first time that we can have a deeper analysis for the corona of a star other than our sun. And also, this is the deepest X-ray image of Betelgeuse ever. So there is other fun science that is still here to look at, even though we did not see a blaring, signal flare from Beetle Buddy saying, "Hi, I'm here, you found me." I like to take these sort of results in stride. There's still interesting science that we can do here, and we still put a very important constraint on a really interesting science question in the span of about 4 months, which I'm pretty proud of, both me and our collaborators who have done a ton of work. I have talked for a while. Thank you very much for enabling me to talk about 2 projects today. I will be happy to take any questions now or later, and thank you again.
Questions. That was amazing. I think we're pretty privileged to have gotten it. So thank you very much.
And yeah, I think unless Jared jumped the gun on me, this may be the first public talk on Beetle Buddy. So
Okay, well, if there's no questions right away, are you gonna stick around for a little bit?
Mhm.
Or you can,
Yep.
Oh, yes.
Fascinating, but I wanted to go back to the previous section of your talk.
Yeah.
I may have missed this, but I was just wondering what led you to make the hypothesis that the buddies or the binaries were blue stars. I just can't remember what the connection was. Can you remind me?
Absolutely. So this is an excellent question, and this actually has some consequences from what I just talked about with Betelgeuse. So the idea there is a similar idea. You know that you have a yellow supergiant, and those are anywhere between 10 and 25 solar masses. So if a star is in a binary, by the time that this one becomes a star, goes to the main sequence, and swells up into a yellow supergiant, the only stars that will be stars by the time that happens are the bigger ones. And bigger stars are bluer O and B type stars. So essentially the only companions to those yellow supergiants that would be main sequence stars that would be in a hydrogen burning phase have to be about 3 solar masses or above, and those are blue stars. However, the existence of Beetle Buddy, a protostar around a red supergiant, is kind of keeping me up at night with respect to that assumption. Basically saying that this is showing that it isn't strange that you can have those lower mass stars. You're just going to try to be looking for these protostar signatures, which is a lot harder to look for. So yeah, from our perspective, I guess what I'll say is that the O and B type stars are the stars that we will be able to see. But based on what we found with Betelgeuse, it's entirely possible that the binary fraction for yellow supergiants, if you allow these protostars in, is going to be a lot higher than what we've initially found here. So
Yeah, could be another category then.
exactly. Yeah, great question.
Thank you.
So, could you have a scenario where you could have, Jupiter sized objects that are, in the binary system with, any star of any age?
That is entirely possible. It is thought in general that there's a distribution to when you have binaries, how different the sizes are. And typically the sizes of the stars are close to each other, but you can have scenarios where the two masses are very, very different. Beetle Buddy appears to be an example of one of them. And yeah, there's essentially a smooth distribution. You go down to smaller and smaller stars, M dwarfs, you get brown dwarfs. And then if you follow that evolutionary line down, you end up at Jupiters. The line between planets and stars is kind of blurred. It's entirely possible. It will be really rare because for physics reasons, there's preference in collapsing gas clouds to make things of similar size. So to make a really big thing and a really tiny thing, it's a little difficult, but I would not say that it is impossible. Yep.
Okay,
I'm just wondering, why specifically the Magellanic clouds were chosen?
That's a great,
General, stars in the Milky Way.
that's an excellent question. So there's two main reasons, and then a third reason that isn't quite as relevant anymore. The two main reasons is that the Magellanic clouds are external galaxies. So when I look at them, I'm going to try really quick to find the nice images that I have. Nope, sorry. Anyway, when I look at the Magellanic clouds, I am looking at that entire galaxy. I know that when I'm looking at that and I'm surveying all the stars, I'm getting every single star that is in that satellite
You're
galaxy.
saying that the telescope that was used, the sensor covers the whole galaxy. Is it?
In a couple of pointings, but yes. Essentially, all of the data that we have from the Magellanic clouds are complete. Whereas within our own galaxy, we are inside of a forest trying to count all of the trees, and we cannot move. Okay, this is the example. This is a photo that I took with my camera when I was down south. That's the entirety of the small Magellanic cloud, and this is the entirety of the large Magellanic cloud. So you fit the whole thing in there, and you know you're getting all the stars. In our own galaxy, the dusty lanes in the core of our galaxy totally block the opposite side of the galaxy from our view. We have no idea what that looks like. The other reason is that because these galaxies are sort of up off the plane, there's not a lot of dust in between us and them, which is good because dust gets in our way, dust dims stars, it changes the way that we think about things. The third thing is that we know the distances to these Magellanic clouds really, really well. And in order to get the true brightness of a star, you need to know its distance. That used to be really, really hard in the galaxy. That has become much easier since the advent of the Gaia satellite. So the distance argument, that was the part that isn't really relevant anymore. But essentially, yeah, those are the three reasons. But the really big one, the really important one is that if I want to get a systematic fraction of how many yellow supergiants in a population have a binary companion, I want that population to be meaningful in some way. If I just take the yellow supergiants that are close to Earth, that's only a little fraction of our entire galaxy. Whereas if I'm looking at these, they're small galaxies, they're little dwarf galaxies, but you know that it's a complete stellar population. So that's meaningful in a way. Like the difference between if you wanted to find all of the redwood trees in a little patch of the forest, or if you were looking at the entire forest, it's a more meaningful metric that you're looking at the whole thing.
So, okay. I understand you're right, that the closest complete galaxy you can observe.
Yes, exactly.
Okay, well, we have two gifts for you. One for tonight,
Thank you.
and as many of you know, Anna helped out with the total solar eclipse, and Randy wants me to make So those of you who remember the last month, we do have member observations, but they're concentrated into just a couple of nights, and most of them were in the last week. Jamie sent us it's not astronomical, but it was still a beautiful shot from Bay Bulls, so I put that one in first. And then no solar images, lots of solar system objects. So I did a shot around the moon in December 10th. So that's Tycho, and that's right there. Jim Stacy, are you online? I was trying to figure out where this was, and I realized that with this kind of setup, this might actually be a very small bit of the moon. I was just wondering if you know where that is, Jim. Still there, Jim?
Yeah, I'm here. I don't know if you can hear me, but
Yeah, we can hear you. So do you know
Yeah,
where this is on the moon?
well, first of all, I think this image is inverted left, right.
Yeah, I thought so too. Just
And,
from the shadows, I figured that out.
Yeah, I literally didn't identify that crater. Sorry.
Okay. Okay. Anyways, it's I think it's an extreme close-up for sure. Okay, thanks a lot. And then David, I don't know, is David online? I don't know if I saw him. Anyways, he sent this one along to us, and just watch, wait for it now. No, there. So he actually caught this image with his sea star a couple nights ago. That's pretty cool. And Sue, so going back to December 1st, Sue got this nice shot of Venus just before sunset. And then on December 4th, we had a flurry of submissions of Venus and the moon. So I'll just run through. Richard, Randy sent one in. John Peddle sent one in. Gary did one. I did one. Chris did one. And Jim did a beautiful one, as you would expect, with you can actually see Earth shine on the dark part of the moon. And then Cynthia did Venus last night. So this is showing us that Venus is still there, but you probably knew that. But that we had sort of a gap there. And Jamie did a shot December 13th. So you can see we only had a couple clear nights. The moon and Jupiter, a lot of people noticed that you know, they were close together, but Jamie got a picture of it, including a halo around the moon. And then here's an amazing picture that Chris did a couple nights ago of Mars. I'll get out of the way. The ice cap up at the top there, just incredible detail. Really cool, Chris. I did one the same. So I will point out this is with a 12-inch and a special camera, a good camera. And so I tried, and also there's a different time. So this is 11 o'clock. I actually tried earlier. There's the ice cap, but this is with a 3-inch, so not as much detail. So that was what we had with Mars. And then a lot of us have been trying Jupiter. So this was December 1st, and that's Io and Ganymede. And this was using the planets that I've done in the past have been with an 8-inch Dobsonian just sitting still, letting the planet go across for about 20 seconds. And as Chris pointed out, that is going to cause a little bit of blurring. And so I've sort of changed over the course of this month, but this one was with the Dobsonian. Chris, this is the same night, and you can see the beautiful detail that Chris gets here. And again, this is Io and Ganymede there. And these are all videos using PIP and then something to do. PIP is Planetary Imaging Preprocessor. And so December 3rd, this was the last time I tried anything with the stationary telescope. And Chris, the next night, again, Io and Ganymede. And down here, Chris, you want to say a little bit about that?
Around then, Space Weather had a photograph as well, and they commented on it. This is a supergiant thunder system, and you asked this afternoon, is there thunder? There's nowhere to hear it. I think there is, but anyway, this is an Earth-sized convection cell from about 50 kilometers deep in the South Equatorial Belt, and just bubbling up through the material in the belt to above it, and that'll probably spread left and right through the belt over the coming weeks or months.
Yeah, we see that actually in a few more of the images that are coming up. So that was December 4th. And so that night I gave up on the using the Dobsonian. So I went back to my 3-inch refractor with a Barlow, and I tried a black and white camera, an ASI 120mm Mini, and you can see things sort of sharpened up quite a bit. And there is the storm there. And then the same night I tried putting my DSLR on, and I started to get better images. And again, this is Io and Ganymede, and there's that storm again. So that's December 4th. December 10th. When I posted this, originally I forgot that I had a star diagonal in, which does that to the image. So I had things on the other side, but there's the red spot, and that is Io and its shadow just coming on. And this is about 7 o'clock, 7:20. And then, so it's 80 millimeter refractor, Barlow, two times Barlow, and then the DSLR and some digital magnification. And then Chris, a couple hours later, IO now has gone off the right side, and the red spot has moved across over to the right side. So those are sort of two images in sequence. That's the 10th. The 14th, I think that's probably that storm coming back on again. That's Europa over there. And then Tim and Sue had a nice shot here with Sue. So the 9.25, that's your telescope that's in Sue's observatory. Lovely shot here. And I guess that's the red spot just sliding off the edge there. So that's what, 3 nights ago?
Yeah.
And then
Sunday night.
yeah, so 2 nights ago, there's Io and Europa, and I actually did several. I forgot to put the time on this one, but I did several, and over the course of the evening, I could see Io moving from over here to over here. So this would have been about 9:30. And so then I also did a few of Saturn. So this is with Saturn, the motion doesn't matter quite so much because there isn't that much surface detail. So this is with the Dobsonian, and that's with the refractor. That's 3 nights ago and 2 nights ago. And the thing with Saturn right now is that it's a few years ago, it was giving us a big show because the rings were tilted quite a bit more, and now they're almost edge on. And I guess, when are they going to disappear? Who knows? Next year, I'm just going to see almost nothing there. But
The last time we went to the rings when they done. It'll be the second time I've seen.
so what's the interval? How long?
27.
Yeah. You kind of outed yourself there. Okay.
Because he's too humble for that. His Saturn stuff made it to the news. They sent a camera crew and they showed him in the daytime emulating what he does at night to point at Saturn, and Saturn image made it.
And what I was actually the filler between the guy who was giving the real story. But
Yeah, but I was looking at the CTV National News the other night, and they had this little window in the corner, and the window had that local piece. This is the national news, right?
yeah, there's a bit of, it was, he basically phoned me and said, can I talk to you right now? And he said it'll be on TV in 2 hours. So it happened very quickly there. And that's why there wasn't much there. So not surprisingly, given the weather and the moon, we have had a couple clear nights, but a lot of moon. So very light deep sky objects this year, but one is the Christmas tree cluster. So just to orient you, it's now getting towards winter, so we're starting to see Orion. So I really enjoy seeing Orion. Lots of stuff, and the Christmas tree cluster is kind of in Orion's armpit, and so it's a hydrogen and ionized hydrogen region, and there's the Christmas tree cluster and the Cone Nebula, and we've had debates before about which is which, but doesn't matter. Bernard got all of it, and he processed it so that it actually looks like a Christmas tree. So I'm not sure, is Bernard online? Okay, well, anyways, a lovely picture and a bit seasonal. And so I always think of that as the Christmas tree because that's kind of the ornament at the top, but but the whole thing could, either that's the cone and that's the Christmas tree, or that's the cone and that's the Christmas tree. And somebody can correct me later on. John Peddle sent an image of the Crab Nebula, so that's M1, sort of towards the, or off the head of Orion, and that's a supernova remnant. The supernova was 1054, right?
Yeah.
And so it's still kind of expanding. In fact, I've seen some videos where sort of time lapse, you can actually sort of see waves moving out through it year over year.
It went through HST data. I somewhere saw online a couple weeks ago when there's enough HST data over the years that you can actually see physical motion of the gas. Just the general.
Yeah.
Crazy.
So this is pretty impressive from C-Star, but it's lots of exposures. I did one of the Pleiades, so again around Orion, go up in this direction. Oh, well, that's what it looks like. So the Pleiades are up there. So you go past Aldebaran and then up to the Pleiades, which are an open star cluster with some dust around. And that gives you this nice blue scattered light. Not a lot of there's probably clouds coming in that night, but I got enough for a little bit. And then Jim sent in Jim sends in things that I've never heard of, so I have to look very hard to figure out where they are. So this one is called the Helping Hand Nebula. LDN, that's a dark nebula. And so here's Cassiopeia. So it's kind of off the side of Cassiopeia. So that's where it is in the sky. There's Polaris. And again, another amazing picture from Jim. I guess the hand is that part there. Jim, did you want to say anything about this one? This is with his 8-inch Raza that we heard about earlier.
I'll comment on your math for my total time exposure. It's incorrect. You can double it.
Oh, what's that? Oh, is it 120 seconds?
Well, it's 1141 60-second exposure, so that works out to just a little more than 19 hours.
Oh, I think I took that number from your post, but maybe I copied it wrong. Okay. But I'll take the blame for it because what the hell? Anyways, yeah. Anyways, again, it's not a huge object, but still a very interesting object, and it's amazing that you're finding all the dark nebula really look great in the 8-inch Raza. So thanks for sending that in.
I think the key thing about this image is taken during full moon.
Yeah.
Filters, Jim? I don't think. Yeah, no filters.
Yeah, full
No
moon,
filters,
no
no.
filters.
That's how. Like, what deity are you praying to do that? That's astounding.
Okay.
I was out the same night trying to point to things. I wasn't taking DSO imagery. I was doing spectroscopic tests. But I actually couldn't point within 10 degrees of the moon because the finder camera was saturating the sky. But that's, like 1 second exposures. I know Cassiopeia is pointing a little bit away, but this still blows me away. This is amazing.
Yep. Pretty impressive. And I think that's it for the observation reports. Robert, you have sent in a sky this month, but maybe what I'll do is just tell people to.
Tell people to spell move for it.
Yep. So I'll just show you it. So Robert prepares one of these and Craig posts it with information about what's visible, the planets. Not much going on with comets. Some suggested. What's that?
New one coming in January.
Oh, really?
Atlas G3.
You promise?
Yeah, it's there. It's going to be.
Look this up.
Yeah. Okay, well, so that's one to look for. Okay, thanks.
Oh, T for Ambrose.
And
Still pretty.
so thanks for preparing that, Robert. So you just go on the website and look for Sky this month. You can download that PDF. And so next meeting is January. Use of Zazu AI to fill the gaps in astronomy. We heard about the new AstroImaging Contest, so I guess you can start sending things into that site, and the instructions, which I guess will get them posted in your subject line. You should have something identifying it as the 2024 contest. And you said there was still one calendar left? So one calendar left. We'll have to arm wrestle if there's more than one person. So thank you all for coming. Now it's our holiday meeting, so we have some refreshments. The cooler has ginger ale, normal Coke, and Diet Pepsi. There's some juice boxes. There's some wraps. There's some crackers and sausages. There's some fruit and some little plates. Some coffee and donuts over there. So please help yourself to some of the snacks. Give us a second to unwrap things. And thank you all for coming, and have a great holiday, and see you in January. Oh, and there are some bags here. If there's any wraps or anything left, I like it all. I don't want to take anything home. I don't think Randy does, so help yourself. If there's anything left, don't take it all right into the kids. But once there's been turned around, help yourself to some wraps or some snacks.